We'll do a little longer problem here. We have a structure. We have a pinned structure. We got a pin over here at the wall. We've got a pin at the base. And then we have an internal hinge right there. And there's a point load on that hinge. You see the other triangular load that's present on the structure. So we've got a picture of a cross section down here. That's going to be the cross section down for the vertical member. Here we've got a picture of another cross section for the horizontal member. So let's see what we're going to do here is we're going to determine the normal and the shear stresses at 2 points, both at point E, right here in the vertical member, and at point D, which is right up there by the pin. And what we're asked to do is find the stresses that act perpendicular and parallel. Perpendicular would be normal to the grain. There would be a shear stress that would be parallel to the grain. And so we're going to see if we can do both points here. So at point E, we've got a 45-degree angle. At point D, we've got a 35-degree angle. So if we want any chance to transform stresses, we need an initial state of stress. So let's go ahead and draw some free body diagrams. We'll go ahead and draw the free body of the vertical member. And we see that we've got a member that has 2 external supports down at A, and also now exposed internals. And so I don't have to put the applied load on point B on this figure. You could think of it as existing on the horizontal member free body diagram. But all we're going to do is actually just quickly prove that this is a 2-force member. So if I spin a moment at B, then we find that F1 is equal to 0. So immediately what I'm going to do is go back to the whole structure free body diagram, take that information with me. I've got point A down there now that we just found that F1 is 0, so that's all that's left. And up at point C, we just have 2 perpendicular forces. So we can use the whole structure free body diagram. I'm going to use a statically equivalent representation for the triangular load. So we can draw a big, huge dashed arrow right there. And that dashed arrow has a magnitude and a point of application. If we choose the point of application to be at the centroid of the triangular load, then the couple is equal to 0. So the magnitude is 1/2 base times height. Its height is 0.9 kilonewtons per meter, right, going all the way down to 0 at point B. So there is the point load, and its point of application is going to be 2/3 the distance of the base from the 0 point. So it's going to be at 2 meters. So what we're going to do is go ahead and solve for F2. The quickest way to do that is just going to be to spin a moment up there at point C. So if we do that, we end up with an equation. It's going to have a few pieces to it, but this is only going to have one unknown, F2. So let's see how this thing comes out here. We've got F2 times 3 meters. Here's F2 times 3 meters. Its lever arm, perpendicular distance to point C. We've got the statically equivalent point load. Its distance is going to be 1 meter. There's its lever arm. And we also have the point load that's going to have a component that's going to have a 3 meter distance. So you can think of breaking this up into 2 components. So it's the vertical component that would obviously have a contribution. So there's our one equation, one unknown. There's our answer for F2. So all we have in this 2-force member is normal force. And so the axial force. So the only stress is normal stress from P over A. And there's our answer for the stress state. This is at point C. And so if we go ahead and draw that, we end up with a very nice, easy picture. All right, again, this is point C. And we would have that our grain lines would be working across at 45 degrees. So our transformation may actually go pretty quickly here. So let's go ahead and take that state of stress and let's go put it on Moore's circle. So on the vertical axis, we've got the shear stress. Horizontal is the normal stress. So our initial state of stress up here, I like to do it in red. It's so important. On the X face, I've got nothing going on. On the Y face, we've got minus 0.747 and 0, right, due to the compression. So let's just go over here and let me just redraw this here for just a second. Let me move this bias over. So there's tau. And let's go ahead and plot these 2 points. We've got a point about right there. That would be the Y point, which would be sitting at minus 0.7470. And the X point would be sitting right there at 0. So we can go ahead and draw Moore's circle from it. And we need to transform 45 degrees, which would be 90 degrees on Moore's circle. So that just actually puts us right there. So if we go ahead and rotate 90 degrees counterclockwise, right, that would be 45 degrees in real life. And so we would need our coordinates. This would be minus 0.373 comma plus 0.373. On the bottom down here, it would be also minus 0.373 comma minus 0.373. So our answer is perpendicular to the grain. That would equal minus 0.373 megapascals. And the shear stress, we would just use the absolute value. So the shear stress would be 0.373. All right, jumping to point D. If we're going to transform stresses at point D, we need the initial stresses at point D. Point D is 2.4 meters from point B. So what we want to do is cut it open. We need the internal forces at that point. So what we're going to do is just cut it right now. And we're just going to have to use this side of the free body diagram. Right? Everything on that side of the free body diagram is black. It's known. So we can avoid those 2 red arrows. So that's going to be the most efficient way to do it. We're just going to cut this thing at 2.4 meters. So let's go down here to the picture. What do we expose when we cut it? We've got a little bit of work to do, but we expose axial shear and moment. Now, we have an unknown height to the triangular load. We know its value 3 meters, right? When that distance was 3 meters, we knew its value. So we need to figure it out now that it's something different. Well, it's just going to be similar triangles. So exposing that, we end up using the fact that we were at 0.9 kilonewtons per meter over 3 meters. And so the question is, what is H when we're at a distance 2.4 meters? So there's our similar triangles. We find that H is equal to 0.72. From that, we can then find the statically equivalent point load, 1/2 base times height. And where it's going to be applied is going to be at a distance of 2/3 of 24. So it would be at 1.6 meters. So let's go ahead and do some statics. So we want to solve for these 3 unknowns right there. And that's obviously going to give us an opportunity to calculate the stresses at point D. So when we use the subscript D here, we mean on a cross section that exposes or contains point D. So those are not at point D, right? Those internal forces only act at the centroid of the cross section that's been exposed. So let's go ahead and solve for one of them by spinning a moment right at the cut. So I'm just going to give you the answers here. It's be a good check that you can do this on your own. There's your answer for MD. Some force is X, gives us a quick answer for the internal axial force. And some forces in the y direction gives us an answer for the shear. So I'm just going to redraw right now the picture of the cross section with point D on it. Right? These all act at the centroid. Right here, the internal forces. This would be a summary of the internal forces. So we've got some units police to come out with here. We got kilonewtons and millimeters. And so we need all of our stresses. We've got a P over A stress, so we need the area. There's the cross-sectional area. We have a bending moment and we have a shear stress, so we're going to need the moment of inertia about the z-axis. So 1/12 the base in relation to the z-axis is 30, the height's 100. We've got a y value, and I like to use absolute values on these, so point D is sitting down there at a distance, right? If the neutral axis, which would be sitting at the centroid, which would be at 50, so that would mean the y value that we're going to use, the perpendicular distance to point D, is going to be 30. And now the all-important Q calculation, where Q is going to equal A star times Y bar. So we've already started it right here. So we took the blue saw, we cut perpendicular to the shear force. That's going to expose the transverse shear stress. And so the cut horizontally through it, I circle down below. That gives A star. Right? On this, Y bar is going to be equal to the distance from the centroid of A bar to the centroid of the cross section. So we've got a little bit of work to do to find those. So A star is going to be 20 times 30. Right? Y bar is going to equal 50, which is the total, right? Minus half of 20 gives us 40. So we've got now an answer for Q, right, at point D, right? And the thickness of that cut was equal to 30. So that's actually that's the hard part here. That's all the setup of the pieces that we're going to need as we calculate the stresses below. So let's go ahead and take a look at those calculations. The normal stress, one of them is going to be P over A. Right? We know the internal axial force is in compression, so I'm going to mark that with a big C right there. You could also use negative, that's fine. Bending stress at point D, we can go ahead and use the right-hand rule. We'd end up using the moment, which would be 388, distance of 30, and the moment of inertia, which is about the z-axis. So the bending stress value is sitting right here, right, from that calculation. Let's go back and take a quick look back at our picture. So we ended up drawing positive moment. We got positive, means we would have compression on the top and tension on the bottom, and point D is on the bottom. So we go ahead and call that tension. Right, shear stress, right, VQ over IT, we just go ahead and calculate that. Right, we get a number. Now that shear stress would be resulting from the shear force. That shear stress would be going up, so that'll end up being positive as well. So the total state of stress, the normal stress, we're going to add the tension bending, the compression from the axial, and we get a total normal stress. Sigma xy is going to be positive 0.133 from its calculation. And so here we are. We're going to put this on Moore's circle. So we've done the state of stress. Draw that on a stress block. Go ahead and find our initial points. So all we need to do is plot our points. So x and y. And we'll go ahead and do those big red here. So there would be the y point. I'll go ahead and put 0, plus 0.133. Go ahead and put the X point on here. Be about right there. So that X point, 4.51, comma, minus 0.133. So we'll go ahead and draw a straight line right between those. And so we see that we have found the center of that circle. So the center is going to be at 4.51 plus 0 divided by 2, just at sigma average. So that's going to be at 2.25. So I'm just going to go ahead and label that. So that sometimes helps me just trying to keep track here of my sides. So that's going to be radius r. Right, that distance vertical is going to be 0.133. Horizontal, it's going to be 2.25, right? I took 4.51, subtracted 2.25, so I got a little bit of round off there. So we've got that r squared is equal to 0.133 squared plus 2.25 squared. It's going to give us for r an answer of essentially the same, 2.25. We've got a pink theta sitting in there. So let's go ahead and zoom in just a little bit. Right, that angle right there is the initial theta. Right, we just need something to grab onto. So I would know that the tangent of theta would be 0.133 divided by 2.25. So that's a very small angle. It's going to be 3.38 degrees. So to hit the grains of wood, and let me just kind of re-sketch up here. There was point D. The grain of wood was about like this, and that was at 35 degrees. So what we want to do is rotate this initial stress state 70 degrees clockwise. So we're going to take this point and end it right about there. We're going to strike from initial all the way to the new of 70 degrees. As we do that, we hit movement of the y point. So that's now x prime, y prime. So what we need are the coordinates of those points. The coordinates of those points will give us the stress at the rotated amount. So let's go ahead and highlight a triangle right here. That triangle right there. So up here, this will be L1. That'll be L2. So I'm just going to redraw this triangle down here. There's L1. There's L2. That's a 90 degrees. And so I know this angle, right? That angle would be the pink theta plus 70 degrees. So that angle is going to be 73.38 degrees sitting right in there. So now the calculation of those is actually going to be quite easy. So let's go ahead and calculate L2 is equal to R times sine 73.38 degrees. So that's going to be 2.16. We got L1, which would be R times the cosine of 73.38 degrees, which would be 0.64. So this is 2.16, and that's going to be 0.64. So the coordinates of our 2 points are right within reach here. So the x location, right, x prime, its new location would be sitting at the center of the circle, which is 2.25. To that, I'm going to add L1, 0.64, and it's sitting down at minus 2.16. So the coordinates of that point are going to be 2.89 and minus 2.16. Up here at y, very similar. The y prime point is going to be the center, and we're going to subtract L1, 0.64, and it's sitting at a positive shear stress. It's up there on the positive above the horizontal axis. So it's going to be plus 2.16. So the coordinates of that point are 1.61, comma 2.16. So to finish, we'll draw the rotated stress state. And so we've taken an element that was originally horizontal, we've rotated it. That was at 35 degrees. So sitting down here is the x prime axis. There would be the y prime axis. All right, that's the location on Moore's circle. That's the state of stress. So in the x prime face, I'm going to put tension. I'm going to call it 2.89. Y prime face, we've got tension as well. That's going to be 1.61 megapascals. Shear stress on the x prime face, we're going to draw a shear stress that causes the element to rotate in the counterclockwise direction. Right? We're coming off of Moore's circle, so we have to use the sign convention sort of in the reverse order. And if I can draw one, I can draw them all. So if you were interested, there's the grain lines. They're sitting right there. So this would be the stress perpendicular to the grain, and the shear stress would be 2.16. There would be the shear stress parallel to the grains. So to also present this with the equation solution, we need our initial stresses that we found, sigma xx, sigma yy, and there was the shear stress that we calculated, and you need your angle theta, which is going to be negative 35 degrees. And here's our initial axes. The grain was at this angle, so we would want to take and align the x prime axis. So this would be a negative slope on the x prime. So we would use negative 35 degrees. And from there it becomes a plug and chug, hopefully not making any calculation errors, but you would end up with the same answer. Not much recourse though, if you don't quite, if you do make a calculator error. We will do one quick one. So there's the x prime stress, there's the y prime, both in tension, and the shear stress. Right? The shear stress is positive, and the way we would do that is on the x prime face, we're going to draw the shear stress in the y prime direction because it's positive. So we end up with exactly the same picture.